Hello. Can you hear me? Okay, perfect. Just gonna wait a couple of minutes before I start. I have sent a team link on Piazza for the discussion for today. So you can join the team and we'll have a meeting there. I think you can also do it through the browser. So it should work on whatever browser you have. But if you can download the app, you can also do that. Okay, so let me know if there are any questions before I begin. What is the time? So we'll try to end this in about 45 minutes to 1 hour, and then we'll have half an hour for the discussion. So about 1:15 or 1:30, somewhere between 1:15 and 1:30. Okay. Should we start? Okay. All right. Okay, so let's begin. We were talking about congruences, right? Oops, my tablet doesn't seem to be working. Let me just try to fix that. Okay, there we go. And right. Okay, so we were talking about congruences, and the question was, how do we solve equations of the type ax is congruent to b modulo m, right? So for example, if you have an equation of the type 3x congruent to 7 mod m, and you want to solve this equation, or 3x congruent to 4 mod 7, and if you want to solve this equation is for x, and if you want to solve this equation, you're looking for a number that 3 times that number when divided by 7 leaves a remainder of 4. This is how you read the equation. So 3 times x divided by 7 leaves a remainder of 4. This is one way of reading this. The other way of reading this is, of course, 4 minus 3x is divisible by 7, right? Because they're in the same modulo class, and we know that if a is congruent to b, so we know this fact that if a is congruent to b mod m, then by the definition of modulo, this just means that m divides a minus b, right? So we want to find some way. Okay, we'll figure that out, Jafar, once we're trying to get, I haven't looked at the teams, and I will try to figure out what the issue is. Don't worry about that yet. We'll try to find some way of fixing it. Okay. Alright, so that's the issue. And so I talked about 2 methods. The first method that I talked about was, just trying out, because mod 7. So the important thing is, if you're talking about mod 7, you're basically looking for a solution in these numbers 0, 1, 2, 3, 4, 5, 6. So x can be any of these values, because in mod 7 really the remainder that you can have is between 0 to 6. Any bigger numbers in mod 7, bigger or smaller numbers, can just be reduced to these numbers just by dividing by 7 and finding the remainder. So there's no other possibilities for x to be. So x can be either this 0, 1, 2, 3, 4, 5, 6, or there's no solution, right? So for a small mod 7, for small m, you can just try out all these values and check whether they form a solution or not. That's one method. But of course, if you're working in a bigger m, so mod, let's suppose 100, then you have lots of possibilities for x, so 0, 1, 2, dot, 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 up until 99, right? So for a mod m, modulo m arithmetic, you are going to be going up till m minus 1. And so if you have lots of possibilities for your x, then this method of just trying out all the values until you find a solution becomes a bit cumbersome, and you would want to find a better method, right? And the other method, of course, that we talked about was to talk about the inverse, right? So if you can we find the inverse of a mod m, right? And so the question is, if we can find the inverse, let's say the inverse exists, so a inverse times a equals congruent to 1 mod m. If this exists, if we can find this, then any equation of the form ax congruent to b mod m can be solved by multiplying by a inverse on both sides, x congruent to this mod m, and the result over here is, of course, when you multiply them, this is congruent to 1, so we can just write x congruent to a inverse b mod m, and that would be your answer, right? So you find this number and you find the remainder when you divide it by m, and that's your answer, right? But the question is, of course, how do we find this inverse? Okay, that's not going to be easy. Okay. Any confusion so far? No? Okay. And so now what we're looking for is, first we need a guarantee, right? The question is, does the inverse even exist? And so we have a theorem that tells us something important. So here's an important theorem. And the theorem says that, if you are solving AX congruent to B mod M, then if A and M are relatively prime. What does that mean? Relatively prime means that the GCD of A and M should be equals to 1. So if they're relatively prime, that they have no common factors and they don't divide each other, then if they're relatively prime, then the inverse of A modulo M exists, and the inverse is also unique. So there's just one inverse in the from the numbers 0 to m minus 1, right? And so here's this theorem gives us a guarantee that if you have two relatively prime numbers, then their inverse is definitely going to exist, right? Yes, we can find them. We can find more than one inverses. It depends on what the GCD is, right? If they're relatively prime or not. If they're not relatively prime, then you can end up finding more than one inverse. Okay. So here's let's attempt a proof of this. And so the proof for this comes from the fact by Bézout's theorem. What does Bézout's theorem tell us? Bézout's theorem tells us that if you have two numbers, GCD of A and M can be written as a linear combination. So it can be written as a linear combination S times A plus T times M. Their GCD can be written like this, a linear combinations of the two numbers, which means that if the GCD of A and M is 1, then I can write 1 as a linear combination of A and M. So I can write it as SA plus TM. Now this is an algebraic equation, and I'm now going to convert it. So the equation that I have is 1 equals SA plus TM, and what I'm going to do is now convert it into mod M, right? So I'm going to find both the remainders on both sides when we divide it by M. So 1 is of course going to remain as 1, and this side SA plus TM, we need to figure out what does this number become in mod M. Now notice that if you divide this number by M, we don't know what the remainder is going to be. It could be anything, right, from 0 to M minus 1. But this, on the other hand, is just a multiple. It's a multiple of M. So if you divide it by M, that means that this is going to be exactly divisible and the remainder is going to be 0. So the remainder is going to be 0, which means Tm is actually congruent to 0 mod M. Right? Are you following this? So if you found the remainder from both sides, then this equation just becomes 1 congruent to SA mod M, because this is simply 0 mod M, and you add anything to a 0 remainder, it's just going to give you SA. Which tells me something interesting. It tells me that this equation that I've found is that I found a number S that when I multiply by a, I get 1, which means this is basically the inverse of a. So we've shown that if the GCD is 1, then the inverse exists, right? Oops, I have put an extra page here. Tilde page. Right. Okay. Any questions? So that's your proof, and of course I have not proven that the inverse is unique. You can try to do that, or you can look up the proof in the book. I don't want to spend more time on that. Okay. And so we now have a guarantee that the inverse exists. Okay, and so let's try it out now. So the GCD, let's try to solve the equation 3x congruent to 4 mod 7. And the first thing I need to do is I need to figure out whether the inverse of 3 exists in mod 7 or not. So I need to check their GCD of 3 and 7. And if I can find their GCD to be 1 if they're relatively prime, then I will be guaranteed that the inverse exists. And so at this point I go for the Euclidean algorithm and divide 7 by 3. So 7 equals to 2 times 3 plus 1, and then I divide this. So 3, remember that this is A, this is B, this is Q, this is R. So the GCD of A and B is the same as the GCD of B and R, and so I divide this B by R. Okay, and so what I get is 1 times 3 plus 0, and this tells me, because the last non-zero remainder was 1, this is my GCD. If you recall the method from the last class, GCD of 3 and 7 is in fact 1. Okay. All right, and so here's the thing. So the GCD of 3 and 7 is 1, and now I can write this as 1. Let's take this equation and let's find the Bezout's coefficient for 1. So what I'm looking for is that the GCD of 7 and 3, which is equals to 1, can be written as a linear combination SA plus TM, where A is 3 and M is 7, right? And so I can take this equation and I can rewrite this as 1 equals 7 minus 2 times 3. Okay, and now I've written 1 as a linear combination of 7 and 3. At this point I will take mod 7 in this equation, both sides, so the remainder of 1, so 1 mod 7 is simply 1 because the remainder is 1, and 7 minus 2, 3, 7 mod 7 is going to be 0, and this I don't know, so I'm going to keep it as minus 2 times 3, and so 1, and this is now in mod 7. So minus 2 times 3 is congruent to 1 mod 7, which means what? That the inverse, this is the inverse of 3. Which part? I'm doing the Euclidean. Why is 1 mod 7? Well, if you divide, firstly, let me answer your first question. The first question is, why am I doing this? The answer is that I'm trying to find the inverse of 3, so that when I multiply that inverse over here, I can get rid of this 3 and I will have the answer for x, right? And so using the theorem tells me that if their GCD is 1, then the inverse exists. And the way to find the GCD is by doing the Euclidean algorithm that we're doing over here, just like we did in the last class. We did the Euclidean algorithm to get to the GCD, and then we reverse it to find the Bézout coefficients of 1 with respect to 3 and 7. And so at this point we found the inverse of 3. Your next question, which was what's the remainder? Why is 1 equals to 1 mod 7? Well, divide 1 by 7. Can you divide 1 with 7? The answer is no, you can't, right? And so this has to be 0, 0, and the remainder, this is your remainder. So you can write 1 as 0 times 7 plus 1. So this is the quotient, and this is the remainder. And since the remainder is 1, then 1 mod 7. This is just 1 is equal to 1 mod 7. Okay, sir, I don't get the last part only. Why did we not make it minus 6? Well, we take it, it's actually minus 6, but it's more informative to keep it as minus 2 times 3. This is, of course, 1 is congruent to 6 mod 7. This is true. But I'm trying to keep it in terms of this, if you remember this, I want to keep it in terms of 1 congruent to s times a, because this equation tells me that a and s are inverses of each other, multiplicative inverses of each other, because they're giving me the multiplicative identity. Okay? And so I try to keep it in terms of 1 congruent to minus 2 times 3. And so I know that minus 2 and 3 are inverses of each other. Does that make sense, Maham? Is there any restriction in writing GCD AB, like there, here A should be 3 and B? I don't get your question really. So the way you do it is you divide the bigger number by the smaller number, right? So GCD 7, 3, the way you find it, even though the result is same, the Euclidean algorithm assumes that you're dividing the bigger number by the smaller number, right? Okay. And so before we start using minus 2, just recall that minus 2, if you're in mod 7, then minus 2 doesn't really, minus 2 should be associated with 0, 1, 2, 3, 4, 5, 6. It should be associated with these, with some of these numbers. So I need to divide minus 2 by 7 and find a remainder, right? Find a remainder, and that's, this remainder should be from 0 to 6. Okay, one way to do that is, of course, just to divide it and write it. 7 is equals, sorry, minus 2 can be written as minus 1 times 7. So minus 1 times 7 is minus 7, and then I add 5 to it to get the remainder, and so this is my remainder. The reason I did this was to keep this remainder positive. This remainder can't be negative. Okay. The GCD here is 1, Dania. The GCD, this was the, at this point we found the GCD. And now I'm trying to write it in terms of the Bézout coefficients. So this is Bézout coefficients. But this was the GCD, because the GCD is your last non-zero remainder in the Euclidean algorithm. And we just found it in one step, right? The first step you found a remainder of 1, the next step, of course, you're going to have a remainder of 0. So the last non-zero remainder is your GCD. Yes, 5 is the inverse, minus 2 is the inverse, and actually an easier method of converting minus 2 to 5 is to just notice that you can add or subtract. So if you want to find, let's suppose an equivalence class, let's suppose, notice that in one equivalence class, when you're dealing with mod 7, the equivalence class of 0 is actually equals to 0, 7, 14, 21, 28, and so on. right? All of these have remainders of 0. The next thing is 1. What numbers leave a remainder of 1 when divided by 7? Well, firstly 1, 8, 15, 22, 29, and so on. Notice something important. In each equivalence class, the difference over here is 7, 7, 7. Even when you have a remainder of 1, the difference is 7, 7, 7, right? And this is true for all equivalence classes, for all the remainders. Which means when you talk about the class of 5, let's talk about when the remainder is 5, what you have is 5, and 5 plus 7, 12, plus 7, 19. And you can also do minus 7. So 5 minus 7 is minus 2. Minus 2 minus 7 is minus 9. Minus 9 minus 7 is minus 16. So the difference is always 7. So if you want to find equivalent, so if you started off from minus 2, and you wanted to find the equivalent remainder from 0, 1 up until 6, what you can do is, if you are in negative, you can add 7 a bunch of times until you get into this range. So if I do minus 2 plus 7, you get 5, and 5 is in this range, so I can deal with 5. But minus 2 and 5 are of course same. 5 plus 7 is equals to 12, right? This is also the inverse, because when you multiply it by 3, you should get the same remainder. So 5 is the equivalent remainder. 5 is the remainder. We are talking about mod 7, right? The inverse that we found was minus 2. But remember, in mod 7, any number that is outside 0 to 6 is equivalent to 0 to 6 when you divide it by 7 and find the remainder. Which is why minus 2 is the same as 5, because you get a remainder of 5. It's identified in this class. Why did we write these negative things? Because even those numbers leave a remainder of 5. So even over here you can write numbers like minus 7, minus 14, minus 21. All of these will leave a remainder of 0 when divided by 7. Over here I can write numbers like minus 6, minus 13, minus 20. If you divide these numbers by 7, you will get a remainder of 1. And so similarly, if you divide these numbers by 7, you will get a remainder of 5. Bezout's coefficients don't need to be positive. They can be negative. If A inverse is 5, then S would be 5 too, right? Yes, definitely. We can say S to be minus 2, and you can definitely use minus 2. The issue is eventually you will have to find it in mod 7. So let's suppose there's nothing stopping me. Let's try it out. I can try it by saying A inverse, or rather 3 inverse. Let's continue our example. And so if I say 3 inverse is minus 2 mod 7, or I can say 3 inverse is 5 mod 7, and let's try to solve it using both the methods, right? So the equation that we were trying to solve was 3x equals congruent to 4, right? So 3x congruent to 4 mod 7. If I use minus 2, let's multiply minus 2 on both sides. Minus 2 times 3, x congruent to minus 2 times 4 mod 7. This is minus 2 times 3 should give me 1 because they are inverses of each other. So I have minus 2 times 3 is congruent to 1 modulo 7. And so I can just write this side as x is congruent to minus 2 times 4 is minus 8 mod 7. And minus 8 in mod 7 is actually just, if you divide 8 by 7, minus 8 is equals to minus 2 times 7 plus 6. So x is congruent to 6 mod 7. So I just have to convert this minus 8 into mod 7 and I get the answer that x is congruent to 6. So I need to divide it by 7 and find the remainder. That's what happens when you use minus 2. Okay, 5 is in the same equivalence class as the inverse, yes. Manahil, the inverse is unique in a sense because we're not talking about uniqueness in terms of all the positive integers. We're talking about all the integers. We're talking about just these numbers. In these numbers, the inverse is unique because the inverse is just 5. So the inverse of 3 is 5. In these numbers, the inverse is unique because every other integer is of course identified with all of these. So in that way, though, it can't be unique at all because 5 is the same as 12 and 12 is the same as 19 and 5 is the same as minus 2. So in that way, though, any inverse can't be unique. But if you think about just these numbers from 0 to m minus 1, then there is only one inverse, and that inverse is 5. So we're talking about uniqueness in terms of the equivalence classes. Okay. Any other questions? Okay, so this is how we do it with minus 2, and we can do the same process with 5 as well. Let's try it by 5. 3x congruent to 4 mod 7 multiplied by 5 on both sides, 5 times 3, x congruent to 5 times 4 mod 7. This is 15, which is equals to 1. They're inverses of each other, so I'll get just 1, so I can write x congruent to 5 times 4 is 20 mod 7, and 20 mod 7, if you divide it by 7, 7 2s are 14, you get a remainder of 6, so x is congruent to 6 mod 7. And again, you get the same answer as the one if you had used minus 2 as an inverse or 5 as an inverse, right? The answer is the same. So what we've learned is that modulo arithmetic can be confusing. You have to remember that the only numbers that you're dealing with are from 0 to m minus 1 are these numbers. If you get any other numbers outside this range, you have to come back to these numbers, right? Keep coming back to these numbers by adding 7 or subtracting 7 until you're in this range. X is equals to 6 should be the answer. So why are you writing 6 mod 7 again? Because in modulo, we have to remind ourselves, Jafar, that this solution is in mod 7. Writing x equals to 6 is wrong, because then you are saying that your equation is something like 3x equals to 4, which is not true. 3x is congruent to 4 mod 7. You're still working in modulo 7 arithmetic, which means all of these numbers are in mod 7. So you have to keep it clear that all of your working is being done in mod 7. 6 mod 7 is also 6. Exactly. Thank you. Is this clear? Okay, so how about we just do one more example, and we can then end the class and move to that discussion. So let's say you're trying to solve. So here's an example. Maybe you can try it out on your own first. So 5x congruent to 3 mod 11. Okay, yes, you'll definitely have to practice. So the first thing, can anyone tell me what's the first thing that we have to do here? Yes, the GCD. And what do I expect the GCD to be? I am expecting the GCD to be 1. The GCD of 5 I'm looking for, so I have to get rid of this 5 from this side, right? So to get rid of the 5 from this side, I need to find an inverse of 5. So find 5 inverse such that 5 inverse times 5 is congruent to 1 mod 11, right? And so the inverse that I'm looking for is of 5 modulo 11. So A is 5, M is 11, and I am hoping that the GCD of 5 and 11 is 1. If that's true, then I can find an inverse. If this is not true, then by the way, then I'm just stuck. So let's try to find the inverse, the GCD of 5 and 11. So I divide 11 by 5, I get 2 times 5, which is 10, plus a remainder of 1, and as soon as you get a remainder of 1, you should know that you're done, right? Because the next step is definitely going to be 5 is equals to 5 times 1 plus 0. So at this point, remainder is 1 and you're done, okay? And so the GCD of 5 and 11 is equals to 1, okay? The GCD of 5 or 11, Jafar, not 5 or 3, because you're working in mod 11. You're looking for an inverse of 5 modulo 11, okay? And so now that you have this, you can use the idea of Bézout coefficients to write this equation as 1 equals to 11 minus 2 times 5. And what this gives me is, it tells me that if I convert it now to mod 11, this equation, then this becomes simply 1 is congruent to 11 divided by 11 gives me a remainder of 0, and this I can just leave as minus 2 times 5 mod 11. And so 1 is congruent to minus 2 times 5 mod 11, right? And so I have the inverse of 5 again, by chance it's just minus 2, but this time minus 2 mod 11, right? And so before finding the solution, I can just I could just use minus 2 as well. So if I use minus 2, the equation was 5x congruent to 3, 5x congruent to 3 mod 11, multiply by minus 2 on both sides, minus 2 times 5, x congruent to minus 2 times 3 mod 11. And so this is of course equals to 1, because we've already found that out, that these are inverses of each other. X is congruent to minus 6 mod 11. And now I just need to find what minus 6 is in terms of what's the remainder when minus 6 is divided by 11. And to do that, I don't need to do any division. I can add minus 6. So remember that if in whatever class this is minus 6, I can find the next number by adding 11, right, in its equivalence class. So if I add 11 to minus 6, right, we're working in some equivalence class, so minus 6 plus 11 is just going to be 5. And so 5 minus 6 mod 11 is the same as 5 mod 11, right? And so your solution actually is x congruent to 5 mod 11. Inverse is not equals to 5. The solution is 5. The inverse was minus 2. This is the inverse of 5. Okay. and so the solution for x is 5 mod 11. And so perhaps you want to verify this solution, right? Let's say your equation that you were working in was 5x congruent to 3, and you had 5x congruent to 3 mod 11. So let's verify this equation. X is equals to 5. Is that a solution or not? Let's verify solution, and the way to do it is like this. 5 times the solution that I found was 5, which is 25. What's 25 mod 11? Well, if I divide 25 by 11, I can say divided by 11 2 times some 2 point something, right? So 11 times 2 is 22, 22 plus 3 is 25, so this is just congruent to 3 mod 11, which satisfies my equation. Jafar, okay, first Dania, I hope I've answered your question by verifying that that's my solution. That if you take 3 mod 11 and if you take 5 mod 11 and you plug it in terms of this, you get 3 mod 11. It's a solution to this equation. Verification, just think of it as plugging in your solution back into your equation. This was your equation. Your equation was 5x congruent to 3 mod 11. And all I'm doing is plugging in my solution on the left hand side and seeing is it true or not. So 5 times 5 is congruent to 3 mod 11, which is 25 is congruent to 3 mod 11. And you can check whether 25 and 3 are in the same class or not, and they are. That is, the remainder of 25 when divided by 11 is 3. So both these sides are actually saying 3 is congruent to 3 mod 11. Again, the reason, Manahil, that we don't leave it as minus 6 mod 11 is because we want the solution to be in terms of the numbers, the main equivalence classes, the primary equivalence classes that we are dealing with. So the solution, if you're looking for a solution in mod m, it has to be in these equivalence classes 0 to m minus 1. So you're going to convert whatever answer you get into these terms. The reason we don't write this is the convention is to write it in one side. So if you've written mod 11 on one side, actually when you write 25 congruent to 3 mod 11, we just write it on one side, but the implication is that both sides are mod 11. So this is actually the same as saying 25 mod 11 is congruent to 3 mod 11. The reason we don't write it on both sides is because it's understood that both sides are working in mod 11. So if this is clear, I will finally answer Jafar's. Jafar, मैं आपको बता रहा हूँ solution. The reason one बचा is because the first reason that there was only one was because you had already found that minus 2 times 5 is congruent to 1. When we were doing this working, you had already known that this was equals to 1. So when you multiply minus 2 with 5, you should get 1. But if that doesn't convince you, let's try it out. Minus 2 times 5 is minus 10, and we want minus 10 mod 11. What is this going to be equal to from the numbers 0 to 10? You can find that by either dividing minus 10 by 11 and finding the remainder, or you can just find if minus 10 is in an equivalence class, you can add 11 and find the next number. So minus 10 plus 11 is simply 1. So the point is that minus 10 is congruent to 1 mod 11. So when you have minus 10x mod 11, you can just write it as 1 times x mod 11, which is simply x mod 11. जी बिल्कुल, mod 11 दोनों साइड पर ही है. ये अंडरस्टूड बात है कि आप दोनों साइड को मॉड 11 में देख रहे हो. I guess that's a bit of a something that they don't explicitly write down, but that's the implication that you're looking for remainder on both sides. कितनी easy. Yes, बहुत easy बात है. Okay, is that clear? I wanted to do the Chinese remainder theorem, but I guess we can leave it at that. If we write 25 mod 11 equals to 3, so it's the same thing. Yes, it's the same thing. The convention is just to write mod 11 at the end of the equation. Okay, let's end this and let's try to figure out MS Teams. I'm not sure why it's not letting you join the Teams. Let me check. I'm going to keep the stream on until we can figure out why. Dim dim dim. Okay, so the guest access is with the team administration. Dum, dum, dum. Manage team settings. Allow members. Guest window, allow guest to create and update. Okay, so where's the admin section? Okay, I'm going to end this. So I don't have a license for Zoom, so we can't have a Zoom meeting. IBA is currently out of Zoom licenses, so they couldn't issue me one. I'm going to end this stream and figure out how to add you on the team, and then I'll just send a message on Piazza. Okay?